Ma'am, I have asked to unmute you so you can unmute yourself.
I think I'm unmuted.
No, ma'am. It's
You're
Raka
audible.
Davade ma'am is also here. Yes, she wants to speak.
Evening, good afternoon, everybody.
Good afternoon.
Nice to hear you. I think
Yeah,
it's been a year, more
it's
than a
been a
year.
long time.
Yeah,
Yes.
it's been a year. So, how is the weather there? It was raining here in the afternoon.
It's very hot. It's hot here today, so it's good. The sun is shining.
Gloomy. Nice. So, I think the time is 6:30.
Yeah, we
Yeah.
can start the lecture now. I will just like to give some instructions beforehand. So keep your microphones and videos off during the lecture. Don't spam the chat box during the lecture. And if you have any questions, you can raise your hands at the end of the talk. And then the host will unmute you and you can speak, or else you can type it in the message box at the end. So, okay, our Astro Club member Surbhi Bajaj will be introducing you, ma'am. So
Okay.
over to you, Surbhi. Yes. Okay, Surbhi, you can start. Yeah.
She's muted still.
Oh, so Surbhi, please, just a sec. Yeah, Surbhi, you can unmute.
Okay, thank you, Anam. So, hello everyone. We, the members of Astro Club of Ferguson College, welcome you all to our online lecture on Reaching for the Sun. Our respected speaker for the seminar is Dr. Helen Mason. She is a solar physicist at the Department of Applied Mathematics and Theoretical Physics at the University of Cambridge, UK. She is also involved in many international projects like Skylab, Yoko, and Soho. We are really grateful to have you today here, ma'am, and we all welcome you.
Thank you. Okay, shall I start now? Can you hear me?
Yes, ma'am.
Thank you. Okay, so welcome everybody. I'm really happy to be here and to talk to you this afternoon. I know it's a very unusual situation, but it gives me great pleasure to talk to you. I'm going to share with you some things that I have been learning about the sun. I've been studying the sun for many, many years. The image that you can see here, I hope, on your screen, is an image taken from the Solar Dynamics Observatory, which is a spacecraft which is looking at the sun from space, a NASA spacecraft. And on the side of the sun, on the right-hand side, you can see a huge explosion on the sun. And I'll come back to that in a minute. But first, I wanted to say that I'm thinking of you all, particularly at Ferguson College. I've been to visit you several times, 2017, 2018. I tried to visit India each year. I wasn't able to visit you last year when I came, but I'm hoping to visit you again next year in 2021. It's been a very difficult time for everybody in the world. It's been a difficult time for us here in the UK. Our university has been closed for 6 months. I haven't been into work. I've been working remotely. But we're hoping that things in the UK are beginning to get a little bit better, and the universities and the schools have started again, and the universities will start again soon. So I'm thinking of you in India because I know that also in India you've been hit very hard and the cases are rising quite rapidly. So I hope that you soon get through this difficult period and we'll be back again in your colleges and universities and places of work. This is some of the members of my team. I wanted to say I don't work alone. I love to work in teams. And here are some of the members of my team. And they are now, some of them working all over the world, in the USA, several of them. And you can see Durgesh Tripathi there. who is a professor at IUCA, and he worked in my group for many years, and he's one of the people that I come to visit often. And Sargam also was a student at Ferguson College, and then worked at IUCA, and then came and did a PhD with me in Cambridge, and then went back to IUCA and is now working at Glasgow University. So many young people. It's a great pleasure to have worked with them all. I have been extremely lucky in my lifetime working in solar science because there have been so many tremendous opportunities and observatories. I study the sun mainly from space observations, solar space observations, although we do also sometimes use ground observations, but mainly from space because we're looking in the ultraviolet and the X-ray wavelength ranges. And here is just a list, a summary of some of the solar satellites that have been available to us in the past 20 years or so. And all of these satellites look at different features of the sun in different wavelengths or looking at different types of observations. And we often have to try and combine together the observations from different satellites to get the most information that we need. I've worked extensively on SOHO from before it's launched, and it's still operational now. Hinode, also more recently, there have been some satellites which go closer to the sun so that we can understand more about the sun and link the sun to what's happening in the Earth's environment. And I'll talk a little bit more about those. I obviously can't talk about all of these space projects, but I will just introduce you to some flavor, some observations from a few of them and what we've learned and what we hope to learn. So let me just start by summarizing the sun. I'm sure you're all aware of this and have studied stellar evolution in your courses at university. Perhaps the sun is just a very average star. It's about halfway through its lifetime. That's about 4.5 billion years old. And it will, in about 6 billion years, it will grow into a red giant and then explode as a planetary nebula, and the core will become a white dwarf. So it's massive and it's huge, and it's quite a long way away and takes light 8 minutes, 20 seconds to reach us from the sun. If you see the sun there, you can see some dark features, sunspots, and that small round sunspot, not quite in the middle, but to the left of the middle, is about the size of the Earth. So you can fit over 100 Earths across the sun, and you could fit 1 million Earths inside the sun. So the energy in the sun is produced in the core by fusion reactions, where hydrogen turns into helium, and a small amount of mass turns into a massive amount of energy, according to Einstein's equation E equals mc squared, where c is the speed of light. So that's the way that energy is produced in the core of our sun, and indeed in the core of other stars. That energy takes quite a long time to get out to the surface of the sun. It goes through a zone called the radiative zone, and then just beneath the surface, there's a layer called the convective zone, where the energy is transferred by convection. And I'll come back to that. The core of the sun is around about 15 million degrees, and that's the temperature required for these fusion reactions to take place. So if I go back in time, I'll remind you of Galileo. He's one of my very, very favorite astronomers, not least because he lives in a beautiful country, Italy. And I visited his house. This is a picture from his house in Tuscany, which is owned by Arcetri Observatory. Now, Galileo was kept under house arrest because of his scientific confirmation that, in fact, the Earth goes around the sun rather than the sun going around the Earth. He used a telescope to look at the planets, and he also studied the sun. Now here you can see a picture from his window. And like us, he was kind of kept in his house for quite a long time. But he did some amazing work while he was there. So it's still possible to do some work even from our homes and houses. Now he studied the sun, and here I say, never look at the sun. It's too bright, it can damage your eyes, it can make you go blind. He projected an image of the sun and then he drew what he saw. And here you can see his actual drawings of the sunspots on the sun. And you can see that the sun is spinning, and it takes about 25 days to spin around once at the equator. It's slightly slower at the poles, taking about 30 days to spin around. So he was the first person to realize that these sunspots, which had been seen by ancient Chinese, were actually associated with the sun itself, rather than just satellites going around the sun or something else. Now, when there are many sunspots on the sun, as there are in this picture here, the sun is very active. We call that an active sun. Sunspots represent areas where the magnetic field is very strong, and I'll come back to that as well. But here you can see many sunspots on the sun, and when there are a lot of sunspots and a lot of activity, we get explosions on the sun, we get solar flares, we get a lot of material shooting out from the sun, and this can impact the Earth's environment. It can cause beautiful effects like the northern lights, the aurora borealis and the aurora australis. But the number of sunspots on the sun isn't constant with time. It varies over time. And here's just a graph showing the sunspot number, average sunspot number, as a function of year. So that's from the year 1900 up to the year 2000. And you can see how the number of sunspots increases and decreases. So sometimes there's very few sunspots, and sometimes there's a lot of sunspots on the sun. And these measurements give us an indication of how energetic, how active the sun is. At the moment, we're at a period where the sun has very few sunspots and is very quiet. So this period of activity is about 11 years. It goes from having practically no sunspots to a lot of sunspots to very few sunspots in a period of about 11 years. So the sun has been observed from many places in the world, and in particular, here's two examples of famous Indian solar observatories. In Udaipur, on the right-hand side, the picture there of the solar observatory in the lake. Beautiful location, and many people studying the sun there, and with PhD students. And I've had the great honor and the great pleasure to have visited that observatory. And I have several colleagues working there. The other very famous solar observatory, very old observatory, is at Kodaikanal in Tamil Nadu. And that was founded a long time ago and has a solar telescope. Udaipur has a very modern ground-based solar telescope, and there you can see the image of a sunspot called MAST, the multi-application solar telescopes, and some very interesting and good results being taken in Udaipur. Now, this is possibly the most advanced telescope we have. It's taken from the National Solar Observatory in the USA, and you can see there, if I can play it again, you can see there a detailed picture of the solar surface. You can see the convection cells as it comes up to the solar surface. Each of these little cells is about the size of Texas or about the size of France. I'm not quite sure which Indian state it would be equivalent to. But these are taken in last year. These are the first light from this very new telescope called DKIST. which is actually in Hawaii, but is operated from Boulder, Colorado. So going back in time again, another of my very, very favorite scientists, astronomers, mathematicians is Sir Isaac Newton. Not least because he worked in Cambridge. He was a fellow of Trinity College and developed many areas of science, mathematics and science. He was very interested in astronomy and he built a telescope. And there's a picture of his telescope there. He built this telescope himself, ground the mirrors. It's a telescope made out of mirrors rather than a telescope with lenses. Galileo's telescope had lenses. This one has mirrors. So he was also interested in astronomy, he was interested in light, and he was interested in colors. When you use a telescope with lenses, sometimes you see the colors and sometimes they're a bit of a nuisance and you want to understand where the colors came from. So he did some experiments with light to understand the nature of light and realized that the colors of the rainbow that you see in the sky come from what we call white light, which is just the light that our eyes are sensitive to, which can split into those colors. He did these experiments with a prism, taking one of the blue parts of the light, passing it back through the prism, or a red part, passing it back through the prism. And he wrote a treatise on the nature of light. Now we can do something which is even better, and that is in some way to dissect the light so that we can understand what the gas is made of. So, for example, if we have light and we split it into the colors of the rainbow and we pass that through a hot gas, we get, using a spectrometer which has a slit, we get these spectral lines, these dark lines on it. And these dark lines are characteristic of the gas which we've passed it through, the elements of that gas. So they give us information. This is called a spectrum of the light. If we heat the gas then emits these lines. These lines are produced when ions, atoms, jump from one energy level to another and give out light, or when they go from a lower energy level to a higher one and absorb light. Now, this is a very, very powerful method of determining many aspects of the gas that we're trying to study. And this is something that I, in particular, am a specialist of. I'm a specialist of understanding these spectral lines. So, for example, if we look at the emission lines from different elements, from hydrogen, helium, nitrogen, neon, argon, mercury, we see they all have different characteristics. And that's how we're able to identify what the stars are made of, what the sun is made of. We're able to look at the light that comes from that ionized gas, that plasma, and then we're able to understand what it's made of. But it's also possible for us to understand other features about that gas. We can also, using different lines, different spectral lines, we can determine how hot it is and how dense it is and how it's moving. So it gives us a lot of information. That's the only way we know the nature of the objects we see in the sky, because we can't go and touch them. So on the right-hand side, that's an image of the sun taken from Skylab in helium emission from helium. And you can see on the side there, you can see a huge eruption on the side of the sun. Now, a total eclipse of the sun is something just quite awesome. It's quite, it's one of nature's wonders. And if any of you have had the opportunity or might have the opportunity to experience a total eclipse of the sun, I would really urge you to do so. Not only is it very beautiful, but it's also very disturbing, because we depend so much on the sun, and then suddenly the sun goes out and it gets dark like nighttime and cold and cool. So it's quite an experience. But here you can see a picture just in white light of the eclipse. And you can see, if you look carefully, and I hope the resolution is good enough for you to see, that it has a lot of structure. So what we're seeing there is we're actually seeing the gas tracking the magnetic field on the sun. And because the gas is ionized, it's showing you what the magnetic field on the sun looks like. So it's very beautiful, and we're able to do some experiments during an eclipse, but also just to enjoy it. So when they had one of these total eclipses, we see that beautiful, I should have said, sorry, the light around there is the corona. What you're actually seeing is a crown of light. It's the atmosphere of the sun. So the moon blocks out the disk of the sun. The moon blocks out the main disk of the sun, which is 1,000,000 times brighter than this corona, this crown of light. So we can only see that when we block out the disk of the sun because it is so bright. So what people did during an eclipse was use a spectrometer to try and understand the nature of the corona. And when they did that, they saw some bright lines in the visible. Now this is plotted in a slightly different way. This is the intensity versus the wavelength in the visible. But they saw a green line, they saw a yellow line, and they saw a red line. And they weren't able to associate those lines with any elements that they knew about. So helium was named after the sun, Helios. It was discovered first on the sun. They invented a new element called coronium, which was named after the corona. Of course, coronium isn't an element that you will know about because it was one of those scientific theories which really didn't go very far because we couldn't fit it into the periodic table. And what they discovered after many years, after about 25 years or so, is that actually these lines that they saw were due to iron. That's Fe, iron. It's normal iron. When you start to heat it, it melts at about 1,500 degrees. When you keep heating it, it becomes a gas at around about 2,700 degrees. The sun's surface is about 6,000 degrees. But actually, that corona that we see during an eclipse is 1,000,000 degrees. Now, what happens when you heat a gas with iron, for example, is that iron would normally have 25 electrons orbiting around the nucleus, but as you heat it, those iron atoms bump into each other and the electrons gradually get stripped off. The more you heat it, the more electrons get stripped off. And in fact, what produces the green line is iron, which has 13 of its electrons stripped off. We call that iron plus 13 or iron Roman 14. And in order to do that, the temperature needs to be 1,000,000 degrees. Now, I should say there's not very much iron in the solar atmosphere. It's mostly made of hydrogen and helium, but there are, we call trace elements, small amounts of other elements, small amounts of iron, oxygen, carbon, all the other elements. I was very fortunate in 2017 because I was NASA's solar representative in the Great Smoky Mountains and was able to experience the total eclipse and also join in the celebrations there. That was just amazing. And here, because it's so frightening, here we see what the Cherokee Indians thought was happening. They thought that a giant frog was actually eating the sun. When people can't understand scientifically what's happening, sometimes they make up mythology or stories. Now, if we look at the sun in X-rays, we see this very hot gas. A very hot, we call it ionized gas, is a plasma, It emits strongly in the X-rays and in the ultraviolet. So when we look at this picture here, which is a picture taken with a camera sensitive to X-rays, of course our eyes can't see X-rays, but the camera is sensitive to X-rays, and we've colored it orange to see what we're seeing, we see some interesting features. At the top, we see a very dark region, top and bottom, and that's where the magnetic field is open and the gas flows out into the solar wind. We call that the solar wind. It flows out, the plasma flows out. In the eccentric equatorial regions, we see very bright regions, and that's where the magnetic field is closed and the plasma is trapped, and that's where the sunspots are. Now, I've mentioned the solar wind, so let's think about what that is. I said it's gas that flows off the sun, and it was first suggested in 1910 by Eddington that the solar wind could exist. And this was suggested because of comets, and I don't know whether any of you recently saw Neowise comet, but the comet has two tails. It has the white tail, which is neutral gas, and then it has a blue tail, which is an ionized trail of gas. And that tracks the solar wind, the magnetic field, the direction of the solar wind. Eugene Parker named this the solar wind, and he produced a paper which mathematically showed how the solar wind evaporates from the sun's atmosphere. Now, people didn't really believe him, even though he got all the equations right. And in fact, what happens when you write a paper is it goes out to what we call referees. Two other people in the community would judge it and decide whether it should be published or not. And the referees actually said, no, this can't be right because this isn't what we think is happening. But Chandrasekhar, very famous Indian astronomer, was the editor of Astrophysical Journal, the famous journal that he published in, and Chandrasekhar overruled them. He said, yes, Parker is right, Eugene Parker is right, there's nothing wrong with the mathematics, he's going to publish the paper. And this paper now is one of the most famous papers in the theory of the sun and the solar wind, the gas that flows off it. So let me tell you a little bit about SOHO. SOHO had many different instruments to both observe the solar atmosphere, to understand the interior of the sun by small vibrations on the surface, and to study the solar wind that flows off the sun. So here is a picture, a movie taken from SOHO with one of the instruments, which is looking in the ultraviolet. We can't see the ultraviolet, so we've colored it any color we like. We've colored it green. This is actually showing us plasma of around about 1 million degrees. And again, you can see the features that you saw on the X-ray picture. You can see the dark regions, which we call coronal holes, where the magnetic field is open and the solar wind flows into space. You can see the brighter regions where the magnetic field is closed, and these are regions where the sunspots are. Here is a picture of the magnetic field on the surface of the sun, and this is taken with one of the other instruments of SOHO with positive and negative polarity. Where those regions are very black and white, that's where those active regions are, where the magnetic field comes out and goes back in, and where those very bright regions were that I was showing you. Let me now come on to a more recent instrument called the Solar Dynamics Observatory. And I showed you at the very beginning a picture that was taken from the Solar Dynamics Observatory. Now this also has cameras which look at the ultraviolet, but they can see the sun in a lot more detail than SOHO could see. And they can take images every 12 seconds. We call that the cadence, how frequently you can take those images. So you can see a lot of detail and they can take images very quickly. and they can take images in a range of ultraviolet wavelengths. And each of those bands is sensitive to a few of those spectral lines, which is sensitive to a particular temperature. So they can get a sample of the temperature at different temperature bands. And here you can see a picture which from the left-hand side goes from 5,000 degrees, 50,000 degrees, 600,000 degrees. Down the bottom is coming up to 1,000,000 degrees. So each of those images is a small band in the ultraviolet, which is sensitive to some of those spectral lines, which are sensitive to different temperatures, going right up to 10 million degrees. Now, when we have a solar flare or an explosion on the sun, we can reach temperatures of 10 million degrees or more. So the Solar Dynamics Observatory, this particular instrument, the AIA instrument, can see these images simultaneously. And this enables us to be able to model different features on the sun, how they're heating, how they're cooling, even small features or larger features. And we can build models on the computers, and then we can compare them with what we actually observe. So if we took the magnetic field on the surface of the sun, and we solve the equations to see what it would look like, extrapolate that magnetic field, this is the sort of complicated structures that we might see. And as I said, this is a real image taken from the Solar Dynamics Observatory, and this is using the magnetic field, which is measured by the Solar Dynamics Observatory. And then you can see these large loops where the magnetic field is closed and the plasma is trapped. And you can see open field regions where the plasma, the solar atmosphere, is able to escape into space. Here's a closer view of one of those dark regions at the top of the polar regions that I was showing you. And a little bit like the Earth's magnetic field at this time in the solar cycle, the magnetic field is open, and you can see those little arrows indicate that the plasma is flowing out into space because it's ionized, it's tracking the magnetic field. It's going and it's able to track along it and flow. So that is what we call the source of the solar wind, the fast solar wind, one component of the solar wind. The fast solar wind goes at about 700 kilometers per second. Hinode is an observatory which is designed to understand what's happening on the surface of the sun and how that relates to what's happening higher up in the solar atmosphere. So it had 3 instruments. It's still operational. It has an X-ray telescope, and I showed you a picture from an X-ray telescope earlier. That was a Japanese one called Yoko. Hinode is a joint Japanese NASA, USA, UK mission. And I've been working with the teams for SOHO, for Hinode. And in particular, I work on the spectrometer. As I said, I'm a specialist in spectra and atomic physics, and I work with the team on the EUV extreme ultraviolet spectrometer called ICE. And here you can see Louise Hara in the middle of that picture. She's in charge of that instrument in the UK at the Mullard Space Science Laboratories in University College London. There's also an optical telescope which looks at the surface of the sun and measures the magnetic field. Now that was launched in 2006, and as I say, is still operating. We're still getting observations and coordinating observations from Hinode. In fact, last week we were doing some observations, coordinating observations with, in fact, an Indian group at PRL in Ahmedabad who have an X-ray instrument on Chandrayaan-2. So we're working with that team. If we take a slit, so we've got a slit there, which samples a part of the sun, then along each position on that slit, we're able to get a spectra for each position along that slit. So it's very powerful because we can, from the spectra, we can determine what, as I say, what the nature, what the density, what the temperature, what the abundance is, what the movement is of the plasma along the slit. With an instrument like a spectrometer, which has a slit, we have to move across an area, and this is called rastering. We don't get the full image simultaneously as we do with the Solar Dynamics Observatory. We have to kind of move across that area. And sometimes it takes a little bit of time to do that, and we have to design special observing sequences. If we know what we want to try and understand, we design a sequence which is specific to the scientific objectives of what we want to understand. And it's always best if we can combine these observations with other observations from what we call the imaging instruments, like the X-ray instrument, the ultraviolet instrument, which takes the whole sun picture simultaneously. So we use the strengths and the weaknesses of different instruments to try and combine together data sets to understand what's happening. This is a little bit of a complicated slide, but all I'm going to show you is this is the team, and we're there in our Chetri Observatory. It's the team of colleagues I worked with, taken quite a few years ago, as you can see, and Italian and people from Italy and people from NASA in the USA. And we're specialized in the atomic physics, and we've built an atomic physics database called Chianti, which is now used universally in solar physics to analyze spectra and also in many other astrophysical applications. What we do is we provide an easy to use tool to which people can use to analyze their spectra, and they don't have to worry about all the atomic physics that goes in the background to try and understand how those spectral lines are formed. So on the right-hand side, that shows you a spectrum from Hinode ICE, the EUV imaging spectrometer, and you can see it has many, many lines from iron, from sulfur, from all sorts of different elements and different lines there, which we need to be able to understand how they're changing, where they come from, what's happening. Now, between the surface of the sun, what we call the photosphere, and the corona, there's a region called the chromosphere. Chroma means color, and it's a color sphere. And during an eclipse, as you can see here, it has these beautiful red colors. So it's the layer between the surface of the sun and the corona. And it's a very complicated layer. Between the chromosphere and the corona, there's another layer called the transition region, and it's very complicated. It's very dynamic. It has these features which look like twisty spicules sticking up. Very complicated to understand it, but there is an observatory called IRIS, Interface Region Imaging Spectrograph, which is dedicated to understanding this particular region. And one of my students, Vanessa, worked on this for her graduate work and is now working out with the team in Lockheed operating this instrument. So the magnetic field on the sun is formed beneath the surface. People think it's formed in the layer between the radiative zone and the convective zone called the tachocline. And then as the sun, as I said, it moves faster at the equator than it does at the poles. This magnetic field gets twisted up. It's formed because we have something rotating. We have a plasma, ionized plasma rotating, gets twisted up, and then it eventually erupts through the surface. And it erupts in these twisted forms, in these arches, which form sunspots and the big loops of very hot material. So if you think of it like this, on the right-hand side, there's an image in the ultraviolet where you can see these big loops of very hot million-degree plasma. And the sunspots are actually at the foot points. So they're like the footpoints of a bridge or something, or the roots of a tree. They go down beneath the surface. And here you can see it's as if a magnet is lying on the surface there. So those big loops of very hot gas trace out that magnetic field. Now, there's a very important process which we think is key in the solar atmosphere, and that's called magnetic reconnection. And this happens when the magnetic fields change their structure. So here we can see the magnetic fields coming together and then recombining in a different way. Now, magnetic fields don't like to be twisted up. So if they come up from beneath the surface, twisted up, or if they get twisted up by the convection on the surface, moving the foot points around, they don't like it. They like to be in a smooth way. They like to, that's what they call the lowest amount of energy. So they like to be in a smooth, low energy state rather than twisted up. As they twist, it stores energy. And when the twist gets past a certain point, they change suddenly with this magnetic reconnection into a smoother form. So we believe this magnetic reconnection stores energy, which can be channeled up from beneath the surface. And then suddenly the magnetic field snaps, changes its configuration to a smoother form, and that energy is released as kinetic energy, that's motion, suddenly an explosion, or heat, thermal energy, when the plasma is heated up to very high temperatures. Now, this can happen in small ways, which we call nanoflares, very small explosions, or it can happen in very large explosions called solar flares. And this is a model that Parker thought about, where the foot points of these loops, these beautiful, very hot million-degree loops, they move about because of the convection on the surface, and they get twisted up. And then they recombine where all those little stars are, the magnetic field is changing and producing small amounts of energy, which we think is heating those loops. So we've done a lot of studies on understanding the heating of those loops, the way in which the energy is channeled up and then released. And we've been able to compare the models that people have made with what we actually observe in the heating and the cooling of those loops. So this is Eugene Parker again, very important person, did some really good work. Here you can see the magnetic field erupting from beneath the surface of the sun, and it's showing you the temperature. So the red is hot, and as it erupts, it recombines, it changes with the overlying magnetic field. And this has produced what we call a small jet feature, which is a hot feature shooting material out into space. And my student Saga, and this was the topic of her graduate work, she was understanding these small jet-like features that emerged close to active regions. And she did some very nice papers to understand the nature and compare it with what the models were predicting. So moving on to really big explosions, a jet is quite a small event. Back in 1859, two observers were looking in the visible, projecting an image, and they saw a sudden brightening in the visible light, which was possibly the biggest flare that we've ever known about. It was because it had an effect on the Earth. The aurora came right down to low latitudes, and it affected a lot of the equipment that they had at the time, telegraph, things like that. We classify flares in different ways, A, B, C, M, X. X is a very big flare, and we think this was a very large flare. Now, if a very large, and there is a picture of a Solar Dynamics Observatory observing a very large flare. This is, again, from the Solar Dynamics Observatory, and this little box is showing different temperatures here, and it's running with time, and in a minute, a flare, there goes a flare, and you can see it's burning out the detectors. Very, very strong emission in different wavelengths at different temperatures. So we're able to track and try and model these flares and understand these flares. Here is an ultraviolet image of a flare. The edge of the sun is there, and then you can see some of these very large, beautiful loops forming very, very hot after the flare. So we have a sort of model in which something lifts off, material shoots off into space, it can lift off, and then we get magnetic reconnection happening here, and this shoots energy back, particles energy back down to the foot points, and we get these beautiful loops forming after the flare. this is referring to an instrument called RESI, which is looking at very intense X-rays, very high energy X-rays that come from the sun in order to understand the nature of solar flares a bit better. We can also get a lot of material ejected into space. Now, this is what we call a coronagraph. It's like a corona. The sun is blocked out, so we can see faint material. But the sun is actually where that white ring is. And this is an instrument called LASCO on SOHO. It's a large angle solar coronagraph. And we see material shooting out from the sun, 1,000 million tons of material moving with very high speeds, up to 2,000 kilometers per second. So very dynamic events. Here you can see material lifting off, and then you see it shooting into space. Now, in this particular movie, the sun has been superimposed. The sun is actually blocked out, just so you can see where it's lifting off. Again, you'll see it lift off and shoot out into space. This is, the sun is very small here. You can see it lifting off and shooting out. This is taken with another satellite called Stereo, but you can see it shooting way out into space. So we're very interested in these explosions that shoot material into space. We call these coronal mass ejections, CME for short, coronal mass ejection, because sometimes these can come towards the Earth. Now, this is not to scale, but here we've got the sun on the left-hand side and we've got the Earth on the right-hand side. And these huge explosions can come and hit the Earth's environment. Now, fortunately, the Earth is protected by its own magnetic field. It has a sort of blanket around it which protects it. But if it's hit suddenly, or it's hit, you know, like a shock hits it, then that can disturb it. And when it disturbs it, the magnetic field around the sun, which is depicted here with the turquoise lines, changes, and reconnection happens in that magnetic field on the other side of on the right, extreme right-hand side of this picture, and particles shoot back down the magnetic field lines, which impinge mainly in the polar regions. And that's how we get those aurora that we see mainly in the polar regions. But these sorts of events can also affect many other things. They can affect satellites. They can cause electricity blackouts. They can knock satellites out. They can damage them. They can cause electricity blackouts. They can affect high-flying aircrafts, and they can be hazardous to astronauts if they are out in space. We call this interaction between the sun and the Earth, we call this space weather, and we need to understand it better. So what have we done? We've sent 2 missions towards the sun to try and understand the interaction of the sun and the Earth's environment better. The first one to be launched was named after that famous astronomer Eugene Parker. It's called Parker's Solar Probe, and this is led by NASA. It was launched in August 2018, and it's called NASA's Mission to Touch the Sun. It goes very close to the sun, and it has already been close to the sun, and it's sampling the solar wind that is flowing off the sun. The launch was watched by millions of people, and in fact, there you can see Eugene Parker watching the launch of his own satellite. Now, this is a very, very rare event. Never before has a satellite been named after somebody who is still alive. So you can imagine how proud he was when he saw the launch of this satellite. And standing next to him is Nikki Fox, who's the scientist in charge of Parker Solar Probe. So it has a strange orbit. Here's its orbit. The red there you can see is the orbit, and it uses Venus to help it to get closer to the sun. It uses the gravitational pull of Venus to help it get closer. So it's already been quite close to the sun several times and has got quite a bit of data back, and several science papers have been written about the nature of what they've observed. It's very challenging to get so close to the sun, and it has to be made out of special materials. Now, the solar wind, I've talked about the fast wind that comes out of the coronal holes, and I've talked about coronal mass ejections that shoot out into space. But there's another component of the solar wind called the slow wind, and we think that that's associated with the active regions and these huge structures, which we call helmet streamers, that come out from the active region. We think again that magnetic reconnection plays a role, and it pulses material into the slow wind. Now, whereas the fast wind is quite steady in its flow, the slow wind is very intermittent. It has bursts. And these bursts can be problematic because they're hitting the Earth in bursts. So we want to really try and understand exactly how that slow wind is formed. So just a couple of examples of what Parker Solar Probe has seen. There were some Nature papers in 2019. It saw a coronal mass ejection, and it saw these very energetic particles shooting into the solar wind, which it was able to study. It linked the solar wind to a small coronal hole, which was on the sun down near the equator region. Sometimes you get that. It was also able to detect something called switchbacks in the magnetic field, where the magnetic field changes direction, and it links these two small jet-like features, and they may well be linked in some way to the sort of features that my student Sargam was studying. So although the sun was very quiet, it still had lots of small-scale activity, much more than they had anticipated they would see. Even though it's in a quiet phase of the solar cycle. So the next satellite I wanted to mention is ESA, European Space Agency's lead, although NASA is also involved. It's a satellite called Solar Orbiter, which was launched earlier this year. It was launched in February, just before COVID started. Many thousands of people went to watch its launch, very successful launch. But when they came back, the lockdown in Europe started, and they had to actually test all the instruments. So during a certain time, they had to test the instruments, that the satellite was going in the right orbit, that it was working, communicating, that the instruments were working, a lot of work to be done. And they did all of that from home, remotely. So the satellite was actually operated not from the operations center in Germany, but from people's homes. And they did it all to time. So it's amazing what people can actually do, even when they're working remotely from their home. Solar Orbiter is very challenging. Now, it will not stay in what we call the ecliptic, which is the plane of the sun and the other planets. It will go higher so that it can see higher latitudes on the sun. So it doesn't just look at the sun in the equatorial region, it will look down on the poles, higher up. But it will take quite a long time to get there. And it also uses Venus to help change its orbit to bring it closer to the sun. So it got quite close already, but not quite as close as Parker Solar Probe. Again, technically very challenging, because if you get close to the sun, you need to use materials which are can stop the heat coming through onto the instruments. Now, Solar Orbiter has instruments which look both at the sun and sample the solar wind. So it's a little bit different from Parker Solar Probe, because here it has an instrument which is looking at the ultraviolet sun, just as the one from SOHO did and the one from the Solar Dynamics Observatory. And these are the first results from July this year, so very recent. They released some results. If you go onto the ESA website, you'll be able to find these results there. And what did they see? They saw small explosions all over the surface of the sun. They called these campfires, like as if you're going on a camping holiday or something, small explosions. And these could be connected with the heating of the solar atmosphere. Why is the solar corona so hot? But of course, they need to do a lot more studies and a lot more detail before they can really understand what these features are. But they're seeing a lot of detail on the sun, which we didn't see before, at 1 million degrees. So just as we had some really new observations of the surface of the sun from Deakest, we now have some amazing observations of the sun in the corona and the response of the corona. And also, of course, sampling the solar wind. So one thing we want to be able to do is to track what we see on the sun with what they measure in the solar wind. Now, I'm particularly interested in an instrument called SPICE, which is on Solar Orbiter, because this is a spectrometer and I love spectrometers. And here you can see a spectrum with oxygen, neon lines, carbon lines. And from this, we're able to determine the abundance of the features that we're seeing on the sun. And when we sample the solar wind, we're able to co-align those or sample the abundances of what we see in the solar wind. So directly trace what we're seeing on the sun with what we're seeing in the solar wind. The abundance of elements isn't the same in the corona as it is in the photosphere on the surface of the sun, and it changes in different parts of the solar atmosphere. So it's a way of putting like a tracer ink into a flow. We're able to really see what's happening. Very exciting possibilities. So if we compare these two instruments, I'm going to finish in a minute because I'm running a bit late. Sorry about that. Parker Solar Probe stays in the ecliptic. Solar Orbiter goes out. We'll see the polar regions. Parker Solar Probe goes very close. That's 5% of the distance between the sun and the Earth, very close to the sun. Solar Orbiter doesn't go as close. When it did its first science results there, it was about halfway between the sun and the Earth, and it will go to a third of the way. And as it does, it will see the sun in more detail. Parker Solar Probe just has instruments which sample the solar wind, and it does have an instrument which sees the solar wind, but Solar Orbiter has instruments which looks at the sun. We call that remote sensing instruments, as well as instruments which sample the solar wind. But the great thing is to use all of these instruments together to get the maximum amount of information. This is the solar cycle coming right up to date. So along the bottom, there is the year from 1985 up to 2020. And you can see how then superimposed on the background is an X-ray image of the sun from Yoko. And you can see the number of sunspots declining. And at the moment, although we are in a very quiet phase, we are still seeing quite a lot of activity on the sun. So I just wanted to finish by saying that, as I said at the beginning, I work a lot with my colleagues in India, in particular at Ayuka in Pune, and visit them each year if I can do. Durgesh now heads that group. Durgesh Tripathi now heads the group at Ayuka and has many solar scientists working with him and has had several solar conferences there. And he is also leading one of the instruments on ISRO's Aditya L1, which will be launched in the spring of next year. So they've been working very hard on that instrument. When I go to India, I also like to work with schools and teachers with Ayuka SciPop. So the instruments on Aditya, I haven't got time to go into the details, but please do find out more about it. It has a whole suite of different instruments. It has a coronagraph. It has the instrument SUIT, which is the one led by Durgesh Tripathi's group, which is looking at the chromosphere primarily. It has X-ray instruments, and it has other sampling instruments on it as well. So here is the instrument SUIT, Solar UV Imaging Telescope, being built at Ayuka, and then it's tested out in Bangalore at the ISRO's laboratories there in Bangalore, because it needs to be put together in a clean room. So that's all I wanted to say. The other thing that I wanted to say was that in recent years, I've been working with schools and teachers here in the UK very actively, and the project that I'm working on is combining science and art. So we take scientists and artists into schools and we run workshops which think about the science, but also then express that in the art. And we've had a lot of really success with that. So I wanted to just mention that. So that's the end. Thank you. So let me just stop sharing my screen. Okay.
Okay, so I see some questions in the chat box. Purva, yeah,
Let me just put
so,
my headphones on because I might be able to hear better then.
okay. So, Purva, I'm asking you to unmute so you can ask your question directly to the ma'am. Just a second.
Okay.
So I had this question, but I think it got answered during the course of the lecture.
That's okay.
So my question was, you said that the magnetic field closes. So I didn't know how it closes, but it got answered since you showed the diagrams of the field lines of the magnetic field.
Okay, so it erupts through the surface, and when it erupts, it's in a big loop sort of formation, and then it sometimes twists up, or and it can then change. The little strands can change, or when it erupts through, it might connect with some magnetic field that is already there. So that's how it changes. But the magnetic field, if it's open, it goes out into
Thank you.
So there is one question on the YouTube by Sarang Bhosle. He is asking, what is the specific reason behind the very high temperature of solar atmosphere than photosphere? What do you think about the theory of nanoflares as a candidate to explain this temperature difference?
Yeah, thank you. Yes, it was a big surprise that the corona was 1 million degrees when the surface of the sun is 6,000. Oh, you have to remember that the core is 15 million. So really, you need to get some way to get the energy up from beneath the surface to up into the corona, and then to release that energy. So it can channel up, and it's believed the magnetic field plays a key role in channeling it up, and then you need to release it somehow. Now, nanoflares is one mechanism where it can be released higher up in the coronal atmosphere. And I personally am a great fan of nanoflares. And that's because for about 10 years now, we've had a series of conferences every 2 years or so, maybe it's more than 10 years, about loops and about the heating of these loops, where we bring together the theoreticians and the observers to try and understand if the mechanism of nanoflares predicts the temperatures and the densities and the evolution of the loops as we see it. And we think it does. We think that now we've had to do a lot of refinements, and after a lot of work and trying to understand it, we feel that this nanoflare heating, for the loops, is significant. Now, that doesn't mean to say that that same heating process is taking place in the solar wind or in other areas of the sun. For those loops, we've seen that. Other mechanisms, there are wave mechanisms. Waves are seen throughout the solar atmosphere, and people believe that the waves could be channeling energy up, but then they need to release that energy somehow, and there are different ways in which they find that maybe that wave energy can be released. You need some turbulence or something to allow it to release.
The next question is from Shravani Chaudhary. Shravani, you can unmute yourself.
Ma'am, as you mentioned at the start of the lecture, that the sun would become a red giant after 5 billion years, is there a possibility, even if the teeniest bit, that it could suffer a different fate from this?
We're pretty certain about that. The way in which we can be quite sure about, or reasonably sure about that, is because we put it in the context of all the other stars that we see in the sky. So I kind of sometimes think of it like being in a railway station or a shopping mall, and you can see people of all different ages, and that's how if you see a middle-aged person, they've grown up from a small child to an older person, and the track they've taken. So the sun is taking, like going along a highway, which we call the main sequence. It's going along a track that other stars have followed. So we know from what has happened to other stars what the likely fate of our sun is. And we know that if the sun were bigger, if it were 10 times more massive, for example, it would go along a different track. It would go along the track of burning up different nuclear reactions, and it would end up having a massive supernova explosion and ending up as a black hole. So that, or a neutron star, that's another track that it can go along. So we can put our sun in the context of what we can observe about other stars, and that's quite important to do that. So indeed, in many ways, because flares can be seen on other stars rotate, and so we can also put it in the context of how big, some stars could have massive sunspots, for example, and then have massive flares. So we try to understand our sun. It's so close and we see it in a lot of detail and we can understand a lot of things about it, but we can understand even more in the context of how we can place it on the pattern of what's happening to other stars.
So the next question is from Viren. Viren, you can unmute yourself.
Hello, ma'am. Yes, first of all, thank you for this amazing lecture. The illustrations, your examples were all very, very perfect and very new.
Thank you.
So I had a doubt that it has been crossing me for a very long time that in our planets there is a reversal of magnetic poles, right? And
yes.
So I was thinking, is there a possibility that there can be nano spots, magnetic spots on Earth or any magnetic field that is like a giant planet or something? Because if that is possible, then it could somehow answer the.
I think the Earth's magnetic field is formed in quite a different way to the Sun's magnetic field, in a sense, because the Earth's magnetic field is formed by the core, the iron core of the Earth. But it's true that the Earth's magnetic field does reverse, but it's over a very long period of time. It takes not 11 years; it's much longer than that. But there are signals that or signs that it might be changing, because the North Magnetic Pole is moving a little bit and things like that. So there might be some indications that what I didn't say was the Sun's magnetic field, when it changes, it starts with a North Pole and a South Pole, and then it changes to a South Pole and a North Pole. So the whole field reverses, and then it goes back again. So it's really a 22-year cycle on the Sun. But the Earth's cycle of reversal is much longer than that. And I'm afraid I don't know enough about the Earth's magnetic field to give you more detail about that. But I do know that it does protect us. So I certainly have some concerns if it's going to reverse. What exactly would happen? Maybe we would still be protected in some way. But but I don't know enough to be able to answer your question in detail.
So I have a question from YouTube also. The question is from Abhishek Kulkarni. He is asking, what is the reason behind the irregularly strong magnetic field at the sunspots?
Okay, well, that's where the magnetic field, lots of strands form in what we call flux ropes. And as they rise up through the solar surface, they form these big arches, like say like a bridge or a big arch shape. And the sunspots are where those foot points are, where it's coming out from beneath the surface. And so it's very strong the magnetic field is very strong in those regions. And then it goes out and disperse, goes in a big loop in the solar atmosphere. Because the magnetic field is very strong, several hundred Gauss in those regions, and it's for quite a long way, like the roots of a tree going down, the convection beneath the surface of the sun is inhibited. It's not as powerful as it is in other regions. So the sunspots get slightly cooler than the rest of the areas on the sun. And because they're slightly cooler, then they appear darker, although actually they're not that dark. They're about the same brightness as a full moon, in fact, but they look much darker compared to the rest of the sun. So there are regions where the magnetic field has burst through the surface, and that's why it's very strong, because it's a big, kind of like a big flux through, like a wire, if you twist a wire up and then it bursts through the surface. So it's got lots of strands in it.
Okay. So, Nihar, you can ask your question.
Oh, that's not very good.
Yeah.
Perhaps just read it out for.
Yeah, okay. I will read it out. So he's asking, is the data gathered by these solar probes available for the public? And
Yes.
could you suggest a project for college students that use this data? Much like how many projects exist for analyzing data from Gaia and Hipparcos.
Absolutely. I mean, all of the data is to be made publicly available. Now, for the Solar Dynamics Observatory, if you want to see what the sun looks like today, that's all publicly available. And you can use something called the Helio Viewer. Helio Viewer, you go onto the web and it will enable you to look at what the sun looks like today. It'll enable you to make movies in different wavelength bands or in different pictures from the sun. It's very powerful, so you can see. Now, the Parker Solar Probe data and Solar Orbiter data, some of it is, Solar Orbiter is more recent, but some is already available, does make all of their data publicly available. The only difficulty is that in order to be able to use the data immediately, you need to be able to understand that data well. And also, there's something called calibration. So whenever you have an instrument, the data has to be calibrated in some way to make sure, you know, what you're actually measuring. It's not immediately translated into something. It has to make sure that it behaves the same in space as it did on Earth and things like that. So there's quite a lot of calibration. So the instrument teams would be responsible for that calibration process. And that's what they were doing, commissioning the instruments during the past few months for Solar Orbiter. But definitely Parker Solar Probe, I believe the data is available. You can see it. You can see measurements of the magnetic field, for example, and the solar wind and other parameters. But you need to do a little bit of work in the background to understand the meaning of that data. Yes, there are people working, and the first people to contact might be some of the people on the teams who you can find out from the websites. ESA is a very good source of information for Solar Orbiter. NASA has a very good Parker Solar Probe website that you can find out more information about that. But in order to maybe make the most use of it, for example, if you wanted to see features moving with the solar wind, understanding the changes that are there, you might want to refer back to what was seen on the sun, so you could kind of track that back. So certainly there are opportunities for projects. I think that it needs a little bit of work, and you would need a little bit of help to do that, but certainly there are opportunities, and the data is all made available. But sometimes, particularly I'd say for the spectral data that I work in, sometimes you need to have quite a bit of background knowledge to be able to understand what it is that you're seeing and doing, and to be able to use what they call the software. But they are making it as available as possible. That should be true for a DTIR eventually, after the instrument teams have finished working on the calibration and things like that.
So, ma'am, we will take only last two questions, if that is okay with you. Ajinkya, you can ask your question.
Oh, hello, ma'am. You have mentioned interior of the sun is described by vibration on the surface of the sun. So can you explain how do we construct interior design, and is there something which we might be missing in the interior design?
Could you repeat that question for me, please, Pradhan? Because I didn't quite.
I want to ask, how do we construct interior design, and is there something which we might be missing in interior design?
Oh, in the interior. Okay, yes. The way in which we measure vibrations on the surface of the sun is when we look at spectral lines, sometimes they shift. I don't know whether you've heard of the Doppler shift. So it's like as if a a car is going around a racetrack. It changes frequency. So from the shift, we can see small motions, and these have to be very sensitive instruments. There are instruments also in India that are doing these measurements, very, very sensitive instruments to measure the vibrations of the gas on the surface of the sun. And then we can build up a whole picture of how the waves, some waves go right through the center of the sun, some just go on the surface of the sun. It's called helioseismology. It's like seismology on Earth, but it's on the sun. It's a very complicated area to work in. You look at all these waves. And what we can do is then they can have a standard model for what they think the sun is like, and then look at how that matches up to what they're actually observing with regard to all these small vibrations on the surface. And initially, when Soho studied this, they did have to modify slightly the temperature that they thought the center of the sun was and things like that. So they do modify things slightly if what they are observing isn't quite matching up to what the model, the standard model that they think the sun goes through. But on the whole, that's the idea. You try to match up what you're observing with what you're predicting should be happening, both from a, say, a standard model of the inside of the sun.
Viren, you can ask your question.
Yes, hello, ma'am. I just missed on one question before. I read somewhere that the magnetic field lines can only be traced till the point where the plasma is reaching. That is, we have one part of the magnetic field line that is invisible to us. So, what if we could, rather than observing the sun, we could send tracer elements to the sun and trace them back? For say like a coronal mass ejection, just what it does is it forms a ray, and we get a fractional picture of how our magnetic field might be looking. So in this way, if that can be possible, then
yeah, I mean that's the sort of thing that they're trying to do with connecting with the Parker Solar Probe Solar Orbiter, connecting what's happening on the sun with what's coming right out, and people will be studying the Earth's environment as well. So again, you would build a model from the magnetic fields on the sun and trace that out and see if what you're observing is consistent with the way in which you think it should trace out from the sun to the Earth's environment. But then it gets quite complicated because there are other processes that might take place en route. So the magnetic field is very, very difficult to measure. We can measure it on the surface of the sun. And what we're now trying to do is to measure it in the solar atmosphere. And it's very hard to do that. But DKIST has another instrument which is trying to measure the magnetic field higher up. So we don't just have to extrapolate. I showed you those pictures where we extrapolate, that is, we just solve the equations. They only work if we can make lots of assumptions. But we actually want to be able to measure it so that we can use other infrared lines are very good at that. So at the moment, we're trying to develop techniques. There was a rocket flight, not a rocket flight, aircraft flight during the eclipse, which was trying to observe the infrared lines, which we could use to measure the magnetic field. That's in the sun's environment. But then when we get further out, it can actually be measured in the solar wind if we take samples. So those satellites can take samples in the solar wind, but they need to trace it back, as you say. And then in the Earth's environment, we can measure it. I saw one question about energy, which I'd quite like to answer. I saw it pop up on my screen. Could I answer that one? I think it was about the energy from the sun.
So the question was from Anchal. I will ask him to unmute. Okay, Anchal, you can ask.
Thank you. I would like to ask, can we consider, while researching on the sun, about the energy, via harnessing of the energy from the sun or its magnetic field?
Yeah, I think that's the reason I like that question is because I think all of your questions have been really interesting. So thank you so much for everybody's questions because they've been really interesting. This is a particularly interesting question. We can obviously harness the energy from the sun, and we do. All of the energy we have here on Earth comes from the sun initially, except for some in geothermal vents. Everything else comes from the sun in one way or another, and of course, solar panels and things. But the energy, the way in which the energy is produced in the core of the sun, from hydrogen to helium by nuclear fusion, people here on Earth are trying to reproduce that process. There's some research that went on in the UK in a jet laboratory with a torus, with a fusion research machine. And there's a bigger project in France called ITER, ITER, which means the way, which is an international project that India is also involved in, which is trying to produce energy for here on Earth in the same way that the sun produces energy. But in order to do that, we have to make it commercial. We have to have a commercial reactor that can be reproduced. Now, the great advantage of making energy in that way is that it's relatively clean compared to the sorts of nuclear reactors that we have at the moment, which use uranium and heavy elements. So there is a lot of work being done on how we could harness the sun's energy better and how we could develop it. Yeah. Could we do it with magnetic reconnection? Maybe, but we'd have to channel the energy from somewhere. Okay, I think I'd better stop there, or I could probably go on all day. I'm sorry.
So in this meeting, we have Professor Durgesh Tripathi with us. So
okay.
I would request him to say a few words.
Hi, can you hear me?
I can hear you.
Hi, good afternoon, Helen, for you, and good evening to Ferguson College Astronomy Club. Thank you very much for sending me this Zoom link so that I could attend this. Thank you, Helen, for nice talk.
My pleasure.
You have become very pro on online talks. I always still find it very difficult to give a talk when I don't see the audience.
But it's hard. It's very hard because
very hard.
You can't get the response back in quite the same
exactly.
way.
You don't see this, particularly with the students. You don't see the faces and their responses, and it becomes very difficult. But it was very nicely done. Thank you very much, Helen, for doing that. The questions have been always at Ferguson College has been very rewarding. Whenever giving a talk at Ferguson College is very challenging also, because you never know what questions are going to come. So that is always a nice experience. You visited this year in February, but it was just a very short visit for the conference, so you couldn't make it to Ferguson. But every year you give a talk at Ferguson, and this year happened again, so that's good. Ferguson kids will not miss that. Also, you very nicely brought out the Indian counterpart in solar physics and the developments we have. So we hope that some of you guys will think about solar physics as a career and contribute in whatever way you could. That will be a nice way go forward. Thank you, Helen. Thanks again.
Thank you, Durgesh. Nice lovely to hear from you. I will visit again. I will visit again next year, I hope.
Yes, that's the hope. Let's see. I think we have vaccines by then, and then we will have no problems.
Yeah, indeed. My pleasure.
So, thank you. Thank you so much. And I express my gratitude towards our HOD of Physics Department, Dr. Raka Dabade, for all the help and support she has provided us with. And I'll hand it over to her.
Thank you.
Thank you. I'm here to thank Helen, of course, and of course Durgesh also for joining. It was he wanted to join by YouTube also, and then we had Zoom also. But it's really nice he came. And Helen, thank you so much. And one thing I'm really missing this time is to give you flowers.
Oh yeah, beautiful flowers.
Or the memento, because I remember in your earlier lectures, the students used to be so enthusiastic. What should we give Helen this time, you know? And I think last time they came up with this tribal sun, remember?
It was Newton, wasn't
Yes.
it? Yeah, very nice.
Yeah. And
Lovely
people who are
presents.
watching, she really likes flowers. So this time she's going to miss the flowers. And anyway, it was really nice over Zoom, and we really missed you this time. We didn't have you in college, and as you said, you'll be coming back soon. So I'm sure the new students who have just joined in will really have a nice time interacting with you next time. So thank you, and thank you, Durgesh again, and thank you, Helen.
Thank you. Thank you so much. It's been such a pleasure to meet with you. And these are difficult times for everybody. And my heart goes out to you all in trying to cope with it. We do the best we can. There are some positive things, but, quite a lot of negative things around at the moment. So, I'm thinking of you all, and we hope we'll get back to normal in not too distant future.
But particularly what happens is when people who are working in these areas, students are really scared because the presentation is really more scientific, but your presentation today was really simplified, so I'm sure they enjoyed that. And I hope from 90 something students, I think, who have joined from YouTube and Zoom, and we hope some solar physicists will be coming
I
up
hope so.
soon.
Yes, indeed. That's good. Thank you very much. Okay, thank you to everybody.
So I declare
and thank you to the people that have organized this as well, for the astronomy club. Yeah, so brilliant. Thank you for all your technical support and help. It makes such a big difference.
Thank you, ma'am. So I declare that this lecture is over, and we can everyone can leave the meeting.
Thank you very much. Okay, thank you. Bye-bye.
Bye, ma'am.